Okay. Sorry for the technical issue there. I'd like to kick off our next session today. Our speaker today is well known in the industry, Tommy ngba from Alfa Laval. He's been in the industry 20 plus years now and is a well-known expert worldwide on plate heat exchangers. As the sales director for refrigeration within Alfa Laval, he's going to present to us the latest developments they have on their side from a product side, and then how those products have then been implemented by end users around in different locations and applications. So yeah, this presentation is being streamed on the Atmosphere platform. So for those of you that are inside the Atmosphere platform, if you want to ask questions, please submit questions throughout the next hour in the chat button, or especially preferably the Q&A section, so that we can then field questions to Tommy at the end of the session. And then in parallel, as previously mentioned, this session is being streamed live on ammonia21.com, on YouTube, and on LinkedIn. So hopefully between those 4 different platforms, Tommy's gonna be able to get his message across to a lot of people around the world. So over to you, Tommy.
Thank you very much, Mark, for letting us have this session with you. And today we are going to talk about industrial ammonia heat pumps. I was thinking it's a hot topic in the industry now. It's not only refrigeration we are talking about, it's also heating. So I share my screen and can start. Okay, yeah.
Yep, absolutely.
Yeah. Okay, so okay then, welcome. Today we're going to talk about industrial ammonia heat pumps and how we can obtain superior energy efficiency with using plate heat exchangers. And my name is Tommy ngba, as Mark was saying, from Alfa Laval. And of course, it's to have high energy efficiency is about having a good set of components that you put together in a heat pump, but also that they are working throughout the lifetime of the heat pump and at the best efficiency. We're going to talk about some aspects that we see as important and what we have developed. First of all, why industrial heat pumps? This is to benefit low-value heat sources around in society, and industrial heat pumps or large heat pumps makes it possible to use waste or any other natural low-temperature heat sources to supply a higher and more useful temperature by reducing energy and fossil fuel consumption. So typical heat sources that we see is seawater, groundwater, but also more and more waste heat from industries and also from refrigeration plants or data centers. And then the higher temperature output could be used in the industries itself for various processes, for dehumidification, evaporation processes, water heating and combined heating and cooling. We see a lot in district heating as well, to supply heating into networks for space and tap water heating, and other commercial buildings for heat space and tap water. This is a growing part of our industry, and the fascinating part is that by using heat pumps, we can take this low waste heat, if you see on the figure to the right, you have a waste heat at a temperature that maybe is not so valuable, and that you can increase to a higher level with a refrigerant circuit, where you have a refrigerant circulating, and where you can obtain the waste heat, and the gas is going through the compressors, and you get a higher pressure, and there you can take out the heat for at a higher temperature. In this case, we are working between in Celsius degrees now. Sorry for that. We'll use Fahrenheit, but on this sketch we have Celsius. Well, we are at the 40 degrees, and we can have an output of 80 degrees hot water, which is much more useful. And that means also that your pressure in the system will increase on the refrigerant side from around 15 bar to 40 bar, or here we talk about 600 psi in this case, if you take American unit. So we are talking about relatively high pressures on the hot side to obtain the temperature we want. This we did with the refrigerant that we like very much, that's ammonia. For this size of machines, ammonia is really a future-proof refrigerant. It's well known. It's a natural refrigerant that we are talking about in this ATMO conference, with a global warming potential of 0 and ozone depletion potential also at 0. Of course, that's already most refrigerants are doing, but the global warming potential is important. And it's also a very efficient refrigerant with high volumetric capacity, and it's more effective and also cheaper than synthetic alternatives. So you can obtain a low total lifetime cost using this efficient refrigerant. But we know that it's classified as a B12 refrigerant and a PED class 1, so it is toxic and moderately flammable. So we need to take care of ammonia in a proper way. But there is no ATEX requirements like other flammable refrigerants. But we need to maybe have a good ventilation and follow the local rules. And copper alloys cannot be used together with ammonia. But still we like it. It's a future-proof refrigerant and very beneficial for energy efficiency. So one example of an ammonia heat pump that we have supplied is an application. We can go into detail later, but to recover waste heat from a data center to feed a district heating network with heat. There is a lot of data centers built around the world, and they need to be cooled. And why waste that out to the atmosphere? Use the heat, take it into a heat pump, and produce higher temperatures that is perfect for other purposes. In this case, for district heating. Something like that is 30 degrees C, 86 degrees Fahrenheit. We can lift to 60 or 90 degrees, up to 90 degrees or more, around that temperature, useful, 158 to 194 Fahrenheit degrees. Going into buildings for their space heating and tap water heating. Perfect example of an application for heat pumps and for ammonia heat pumps. For those duties, Alfa Laval has developed heat exchangers over time that are perfectly to take care of reliable and efficient duties as evaporators and condensers. We have a range that is going from low capacities to very, very big capacities of megawatt size. For the evaporator size and for the condenser size. And condensers lately we have developed for the higher pressures and higher development in the recent years. We reached 63 bar on 900 psi. Then you can heat water to 90 degrees or more. And also our product have developed so that they can cover for high temperatures that is needed for the heat pump. From the low refrigeration temperature to the high heat pump temperature, so maybe 150 degrees temperature of the gas from compressors is needed. Okay, how can further the semi-welded assure and the superior increase of the COP? First, we must look at what are the positions of the heat exchangers. The most important two positions are the cold side, where you have an ammonia evaporator with the heat exchangers, and then you have the hot side, where you do the heating supply as a condenser, we can call it in this case. But this machine is not run for free. We load the compressor with electricity power. And how do we calculate the efficiency? Yeah, it's the COP. And if we are only talking the heating part, the COP would be the heat energy supplied on the heating side, divided by the electric power that we are consuming from the compressors. So if we can increase this ratio, either by reducing the electricity power or get more heating out of the machine, of the heating supply, we can increase the performance. So we're gonna look at the two positions: the low side where we have the heat source, and the hot side where we have a heating supply and our heat exchangers are incorporated. On the cold side, we have a heat source that we are going to extract heat from a higher temperature to a lower. And while doing that, we are evaporating ammonia. And here, one of the most important things to increase the efficiency is to be able to have a good close approach. And our semi-welded plate heat exchangers has been developed to assure that we can have a closer approach than any other technology. So we can typically raise the temperature of the evaporation of the ammonia side by 2 degrees compared to, for example, a shell and tube type heat exchanger. And for every K we raise the evaporation temperature, we will save 3 to 6% of the heat power consumption. So the compressor would save that energy, or we could use a different size compressor. That's a very important factor why to use a plate heat exchanger in the heat pump. We talk now the cold side. Try to take out the most of the heat from the source you have at the highest possible evaporation temperature. That will increase efficiency. On the hot side, we also want to extract as much heat as possible, and that's typically done by not only using the condenser function, but cool the hot gas from the compressor in the superheater, where you have gas that you are cooling from the highest temperature down to condensing starting, and then condensing where most of the energy is transferred to the subcooler. And subcooler is also a free energy that you can use to increase your overall efficiency. Heating then the source that you want to heat through the 3 stations to the temperature required. This is typically done in the past, and most of the cases, by 3 heat exchangers that are running in series: subcooler, condenser, and the superheater. And that's fine. You can obtain a good efficiency in with this type of setup of the heat exchangers. But our latest development has been to develop this plate heat exchanger with what we call the subcool condense. So we have a functionality, or we have a feature in the heat exchanger that is designed to be able to do the 3 duties in one. This would keep or secure the high performance. We'll come to that later, how we can do that, secure that, but also that we avoid a lot of piping and have only one heat exchanger. So this we developed on the T10 EW size condenser, and we call it subcooled condense. And what you can see here is that we have this is a temperature graph, and you have the meeting air that is heated, and here we have the superheating, condensing, and subcooling of the ammonia, just showing that this is done in one heat exchanger over the plate in the plate heat exchangers. So it's enabling high efficiency of the heat pump and avoiding use of multiple heat exchangers on hot side. And this is now a top seller of when we talk about hot side heat exchanger for ammonia heat pumps. How could we do it? It's not just saying you do a heat exchanger and you do it. You have to have assured that you have a very, very good distribution over the plate width to be able to be sure that you have the superheating area, you have a condensing area, and the subcooling area in the heat exchanger. You also need to have a good distribution throughout the plate pack, and there we have constructed this omega port that allows good port pressure drop, allowing the flow to be spread all through the plate pack. And the curve flow distribution area we call, to be sure that we distribute the gas inside the heat exchanger. So this is built in, and for that type of condenser. And here you can see what can be gained from that. We have the heat exchanger again here inside the heat exchanger. You have the heating media. You have the superheating, the condensing, and the subcooling. And in this case, we can we can lower the condensing temperature as close as, really closer than ever before was possible. You could get an outlet temperature of the heated media that is about the condensing temperature, at least, maybe something even higher, in one heat exchanger. So this is what we call the subcooled condense. And for every degree lower condensing temperature we can have, getting closer here, we can save 1 to 3% of the heat pump power consumption. So normally you would be above the condensing temperature with your, you would have to raise this condensing temperature quite a lot if you're not using the heat exchanger with subcooled condenser built in. So that's a news, and I have a video. I don't know if it's possible. I give it one chance. If it's not working, then we will just wait and we take the next slide. But this is a little film that shows the subcooled condense in a heat exchanger. We open the heat exchanger to look inside. We have the temperature profile to the right. And here we can see the cold water coming in, for example, being heated from 40 to 80 degrees. And on the other side, we will see now how the hot gas from the compressor, ammonia gas coming in, being the superheated, condensing, and in the end it's liquid that is subcooled coming out of the heat exchanger. That's how we can do that in a very compact, very small charge of ammonia as well.
Very cool.
Yeah. Did you see that, Mark?
Yeah. Well, it was really nice, really nice.
Good. Okay. So now I'm going to go into some examples. We have been working and delivered heat exchangers to heat pumps in many parts, but Denmark has been on the front edge. They have for example, you can see the map showing all the heat pumps for district heating that are installed in Denmark and were installed, because this is still 1-year-old map, but they are continuously added to the district heating network. And we have supplied heat exchangers to many of these, but also to industrial process sites in Denmark. I'm going to show you a couple of examples. This one, for example, was inaugurated already back in April 2019 in Copenhagen, a 5 megawatt full-scale ammonia heat pump. They call it a test because the real need for Copenhagen is, of course, much more than that. But this plant was servicing 1,100 households, and the heat source used was seawater mixed up with a wastewater stream that we could use that would raise the temperature a little bit and help us to get a better COP. The power source to the compressors were windmill electricity. So we could say that it's a complete fossil-free heating, and the COP 3.2. So for every electricity kilowatt sent into the plant, you get 3.2 heating out. And you can see there was quite a tight temperature program, because in winter we have only 4 degrees C of seawater temperature, even if we added a little wastewater, extracting heat to 0.5 degrees. And then on the hot side, heating, district heating, circulating water from 60 to 80 degrees, no, 50 to 80 degrees. And we did that we had one semi-welded evaporator, condenser, and here we didn't have the combined subcooling. So we had an additional unit for subcooling to increase the efficiency. But this is a nice and neat way to see how we can heat large part of our society with using a natural waste heat, like seawater or wastewater heat. Another district heating company in Broegger installed the groundwater heat pump 4 megawatt, and it's been running quite well since 2016 already. But they use a 250-meter deep groundwater at 9 degrees, so it's 48 degrees Fahrenheit as heat source, delivering district heating supply of water at 70 degrees. And that means that it's delivering totally 18,000 megawatt hours per year of heating. And Alfa Laval supplied semi-welded plate exchangers as ammonia evaporators, covering the groundwater from 9 to 2 degrees, evaporating ammonia. So COP of heat pump was 4.1. So here we had a little higher. I would say today most heat pumps try to achieve 4 COP4 or more, and with the help of our heat exchangers, this can be raised in the future even further, we hope. And here you have combined cooling, and this is interesting because here we are using not only the heat, but we benefit the cooling of a process at the Grundfos factory in Denmark. And this system builder ECS installed a cooling capacity of 2.85 megawatt, used as a heating input to the heat pump, and then could produce 3.6 megawatt of heating yearly to the district heating network. So we are supplying the semi-welded heat exchangers as evaporators to recover this heat from the heating process. Now on one more, and then waste heat recovery from a brewery process. So here you have a process in the brewery where you can recover heat, and we do that by evaporating ammonia at 12 degrees. And then the heat pump is delivering hot water from 45 to 70 degrees. And this is the heating capacity was 7.5 megawatt. Just take out this low value heat from the process, COP of 4, and we delivered here evaporators and condensers into that set, and it's just now installed. But it shows how it's possible to do fossil-free heating, and it's a kind of electrification on industrial basis as well. Then you have the product installed. That's not the end of it, because we need to be sure that we have a long lifetime operation and efficiency over time. And one important thing is you can see the semi-welded plate exchangers, which is a very reliable technology using welded cassettes, plates that are sealed off, that are sealed with weld on the higher pressure side, typically the ammonia side, and with gaskets on the open, on the water side. And that means that you have a lot of advantages. You can retain and take up any variations of temperature and pressures, because it's a flexibility into this construction. But it's also possible to open and clean if you have need for that. But one important thing is that between every cassette of the high pressure side, we have a ring gasket to seal off that. And that is a very critical part, especially when we come to the higher temperature and pressures. That's why we have developed this ref-tight with a full supported groove, and that is smooth. And with gasket material also developed for high temperature. So a very special part of our development, important for reliable operation over time and then get an extended lifetime. But as I said, when you go to the cold side, we're having seawater, we have dirty water. It's important to select the right material of the plates or the heat surface. And here we have 3 standards. We use 3 or 4 when we have complete clean liquids. But if we have seawater, then titanium is the one to choose. And 316 could be for the intermediate or higher temperatures duties. But these are standards. And our heat exchangers, when you clamp them together, as you saw on the film, it's important that you can open them easily, and we have always ball bearing rings so that it's easy to open and close, to do the service, to clean if some dirt enter and so on. I mean, the cold side is really sensible on the heat pump because if you use some liquids that are more dirty than others. Yeah, and also throughout the operation, the efficiency can be kept also by assuring the same type of distribution we talked about of the plate type. For efficiency reason, we also can use that on the water side because this will clean the surface, self-clean the surface, and you will not have dead spots where you could have fouling, and then the efficiency would fall. So it's not just new brand. You have to think over time as well to keep the efficiency high. And there could even be, we could also help you discuss and come suggestion how to service the heat exchanger over time, to do connectivity measurements, to detect fouling and other risks of the heat exchangers, and maybe also what are the best options when it comes to inline filters or port filters, and especially when you have sea and river water as a heat source, we need to have some kind of backflashing to be sure that we flash out things, animals, small snails or whatever coming into the plant, and that should be done then timely, really often, to maintain the efficiency of the heat pump. This we have and can discuss with you. So summary of the benefits, what I'm talking now is that you have to look at the lifetime, you have to look at the operation over time, and for when it comes to heat pumps, efficiency is what pays back the investment. It's energy here. It's important to have a superior energy efficiency. This is possible to obtain with plate heat exchangers because we have close temperature approach. We have a turbulent flow that keeps the efficiency high over time and also clean the unit. They are compact, so we can save space. We can also integrate different functions into one heat exchanger. Keep the ammonia charge low, which is always a target, I think, as we have this media, and that it's reliable and easy to serve over time. That's what we call superior energy efficiency. So heat pumps are vital for a sustainable energy system, and plate heat exchangers for high efficiency is the focus of our company. And we are not only focusing for this industry, but for all kinds of industry, energy efficiency, to be sure that we reduce emissions, like using natural refrigerants, clean energy, and the circular economy. And ourselves are working on how to be carbon neutral over our whole supply chain, so including our suppliers and our own production by 2030. So that's a challenge we put to ourselves. So let's work on this together. That's what I had today, Mark. Thank you for listening.
Thank you, Tommy. All right, so let me write this down. I've got a few questions for you. Mm-hmm. So are there, this is the moment when participants on the Atmosphere platform, the attendees right now, can submit some questions in the Q&A section. And then Tommy will do his best to answer those. In the meantime, I have a couple. This is a clear direction for your company, right?
Absolutely, yeah.
And this, you know, when you were talking about the integrated subcooling into these plate heat exchangers, how did you manage that within your company? Because I'm guessing that must have cannibalized some of the other sales that you have in your business, because you're eliminating some heat exchangers from there, right? How did you handle that? I'm curious.
But that is for every technical step you take, you you reduce, you improve, and it means energy efficiency takes out some material. But I mean, we have to look at this sustainable. It has to be as efficient as possible. We take the steps together. More applications can benefit from this. Maybe they can afford it in the same.
Okay.
That's right.
So I'm guessing there's a premium to these.
So there's a premium.
There's a premium to these latest generation heat exchangers.
Yeah, there's a premium, but still there should be a win-win, right? So the customer should find that this is the user should find this good. I mean, then you grow also the opportunities for entering new applications which are more price sensitive. So yeah, definitely.
Okay.
Yeah.
And then you talk about how one of the benefits is lowering the charge of ammonia. Can you be a bit more specific about how that works and what examples of how much charge you've reduced by using one of your latest generation heat exchangers?
Well, we typically say compared to a shell and tube, it's a factor of 10. So I mean, that's the first big step you can do.
Mm-hmm.
Then depending on how the rest of the system looks like, you can get down to, we talk about below 100 grams per kilowatt of ammonia. So it's amazing.
That's extremely low
reduction you can do on ammonia charge.
100 grams per kilowatt.
System, how it looks like. If you have a critical charge, or if you have a but for a heat pump, I think a critical charge will be the one that you would design for.
Okay, and then on the servicing side, you showed how easy it was to really open up the heat exchanger, go in and clean it. I mean, that was from day one. The thinking was, how do you optimize the servicing of these heat exchangers to improve their lifespan? But can you at least say, with all the different projects where you've had these installed, can you show that there's been less servicing needed overall thanks to this latest generation product?
No, not yet, because we talk service intervals. Normally that should be years. So I cannot say.
Normally it's like 3-4 years.
Yeah, absolutely. Yes. I mean, it depends on the place where the installation takes place, of course.
Okay.
But if we take the measurement, the different measures to reduce the incoming, dirt or fouling particles with filters, and these things could take away already a lot, right? And then it's just to keep those systems running. Then you can protect the equipment for quite some long time. But what is good with this unit, if something comes and something happens, you open it. You can do that, and it's not a matter of months. It's a matter of hours. I would say maybe days to do that job, right? So
it's a lot more user friendly in that respect.
Yeah. So it's
which is a big deal.
You will not close down your whole heating plant for long, right? So that's
which is a big deal. Especially when you've got a lot of homes that you're trying to heat in the winter. All right. Then the carbon footprint. You mentioned, I think it's actually your last slide. You talked about.
It's a company target.
Yeah. So you want to be carbon neutral over the supply chain. So that's scope 3. So that's really, not just you, but also your suppliers. Carbon neutral. How on earth are you going to achieve that within the next, what year are we? 2028 years? That's a huge challenge.
It's a huge challenge for us and our suppliers, for sure. Yeah. Yes.
But does that start also with what you're doing in terms of the carbon footprint of manufacturing of these heat exchangers? Have you looked into that? Are you reducing the impact, and can you demonstrate that?
We have, for example, installed a heat pump so we can reduce our heating bill. But I mean using some of our energy in the factory, for sure. Yeah, that's.
No, I didn't mean in terms of that. I meant in terms of the actual materials that you're using for the manufacturing process.
Yeah.
The titanium, where's that sourced from?
Yeah.
For example, where have you looked at the carbon footprint of that?
Yeah, but you have to do that. I mean, for example, titanium is now specific, it's a smaller share, but our biggest share is, of course, our steel. And how can you get carbon-free steel? But this is we are putting as a challenge to our steelworks, and steel suppliers, that this is what we are looking for, and we hope that they can they can match that. They are.
And how are they doing that? How are they doing that? Because that's the next wave, right? We're going to be, if you're going to be pushing that through the supply chain.
Electrification of the steel factories. Yeah, it will be interesting. Yeah.
Okay.
But there are the frontiers in this industry. They also have those ambitions. So.
Okay.
Should be able to benefit from that. Yeah. Mm-hmm.
Okay. All right. Let me see if we have any questions raised. All right, now's the moment. If anyone wishes to raise their hand, they can as well. An attendee can raise a hand
or chat
or ask a question. Oh, is this the post-lunch lull?
I was so clear that it was, but of course, people are welcome to contact us.
No, we got one. Okay. We got one. Let me. Okay, so we got a comment from Anders Yule, who you know well. He says, "Good presentation, no questions here."
Good. Okay. Good.
All right, thank you, Anders, for that. Are there any other questions from other people or comments?
I guess this presentation will be available also on your live stream.
Yeah. We'll distribute it to everyone.
Is there a box there where people can? Yeah. No.
Yeah. I have a hand up. Mm-hmm. So how? And now I need to know how. So someone's raised their hand. They want to ask you a question. Let me find out how on earth I'll let them ask you that question. Okay. Benoit Rodier. Okay, can you unmute yourself, please?
Here we go.
Hello. Yes. Hello, Benoit. It's
How
not
are
too
you?
early for you. I'm good.
Yeah, it's early. I have a big question. On some occasions, we have experienced major scaling with plate and frame heat exchanger when we're using a cooling tower. Mm-hmm. In your case, you slightly address like the cleanup and stuff like that, but in more details, is it a real challenge? Is it something that could prevent the usage of river water, lake water, or an open water loop that, within like 2-3 months or 6 months, you're completely scaling your plate?
Yeah. Well, there are different type of fouling and scaling, and for each of them there is a counter measurement. But for scaling, for example, if it is like lime scaling, then the CIP cleaning, you have to make those planned and regular, right? Depending on if there are particles, then there are other counter measurements of filters or something, port filters, for example. So there is countermeasure for everything, more or less everything, but we could at least look at different cases to be sure that we have the best measurement and measures to counter act. Okay. Have you a specific cooling tower for industry, or is it for HVAC or?
A few years ago, we had a major problem with a plate and frame, ammonia on one side and cooling tower on the other side, and it was completely plugged within 3 months. Yeah. Right now, we're planning to use your braze plate APX 112 on CO2 on one side with cooling tower on the other side, and it's raising some concerns on our side. Now, a lot of time you're talking about heat pump that will be like on sewage water, on seawater, on lake water. So,
there is we have different plates also. If it's really, it comes at a cost, right? If you have very dirty water, then maybe you need a wider channel, and then you will have less efficiency. But rather, I would see that we take out that as much as possible before the heat exchanger. Then you can have the best channel and the most efficient condenser in this case. So we should have a chat with our service engineer and the people that work with more specialists in this, depending on the media or what type of dirt we have.
Okay, thank you, Tommy.
Thank you.
Thank you, Benoit. I guess Tommy and Benoit will follow up separately as they know each other well. So, are there any other questions from anyone in the audience or anyone wishing to raise their hand? Now's the moment. Otherwise, it can't be said that you weren't given the chance to ask. I mean, it was an excellent presentation, very thorough. So, and as Tommy said, it will be shared. Can we get the video as well? That would be really cool.
Of course, yeah.
Yeah, we'll share that with everyone. That will be really cool. I think it's a beautiful video. Makes it very clear.
Yeah.
So, all right, okay. Well, I guess I'm not going to ask any more questions. I've already bombarded you. So, there's one from Anders.
Again.
Go on, Anders. He has to say something. Go on, Anders.
No. Hi, Tommy. Thank you for the presentation. It was super good. So, Tommy, I know that this was around ammonia, and I'm, of course, using most of my energy within CO2. I think I miss a little bit sometimes some components where we integrate more functionality. And I see the plate heat exchanger being an obvious choice. Now, Mark mentioned before this about having the subcooling, and then you take away some of your business. But it would be really cool to see some solutions from Alfa Laval or one of the others where we integrate more functions, like having valves in a manifold kind of solution that would allow us to build our OEM systems slightly smaller. Is that something that you guys have been thinking about, or do you see any challenges in this regard? Thank you.
Yeah, very, very good question. I know there has been, like we could call it concept research to integrate, for example, expansion valves and so on in the heat exchanger. I think the industry also we have to get together with other component suppliers to find out the best solution. With this solution we have now with the subcooling, we have been in fact cooperating with some control equipment supplier as well, so we know it can be done because it requires a little bit from control as well.
Okay.
Yeah.
Thank you.
Yeah. Thank you.
Yeah. Brilliant question, Anders. Thank you very much for that. All right. We've got time for one more, if anyone's willing to ask. We got a comment from Thomas Kane saying very interesting. Thank you, Tommy.
Super.
So that's a good feedback for you there.
Yeah, thank you.
Okay. I don't know if there's anyone else fielding questions on LinkedIn or YouTube, and I don't have enough screens to be able to check.
But we
right
just
now
send me
the
the whatever you can, and we will get back to the different people, and we're sure that they have it.
All right. Well, then I just want to thank Tommy for taking the time to present his integrated solutions for heat exchangers, and yeah, very interesting.
And promoting natural refrigerants, yeah.
Yeah, absolutely. Otherwise, you would not be participating. Yeah, we would not have let you in. Renato Riccardi says, grazie, Tommy. So probably someone that you know.
Yeah.